So this is the question of discussion. You have to design a Butterworth low-pass filter, which is having minus 2 dB passband attenuation, and it is at a frequency of 20 radians per second, and at least minus 10 dB stopband attenuation is required at 30 radians per second. So if I draw a response, it's in analog frequency, it's radians per second. It's 20. At 20, we know that at a frequency of 20 radians per second, we need minus 2 dB. So this is 0 dB. This is minus 2 dB. So you can write your alpha p, right? Your alpha p is 2 dB. And omega p, passband edge, is 20 radians per second. So that is my conclusion from the first point. Now the second point, I need at least minus 10 dB attenuation. So stopband attenuation should be at least. That means this value has to be minus 10 dB at a frequency of 30 radians per second. So what is my conclusion? Alpha S is 10 dB and omega S is 30 radians per second. You should be very, you have to see the sign, okay, very peculiar in selecting the sign. They should be, even though it is given as minus 10 dB, you have to take alpha S as positively, because we have formulated the equation accounting this minus sign already, right? So you do, again, you don't want to substitute it. Now, what is the first step? We usually complete the design in 2-3 steps. The first step is computing the order, right? So the first step is computing the order. So we'll use the equation of order, log lambda by epsilon divided by log omega S by omega p. So I don't know the value of lambda and epsilon. I know omega S and omega p directly from the question. Now let me find the value of lambda and epsilon. So for lambda, we have the equation. Lambda is a specification corresponding to your stopband frequency. So 10 raised to 0.1 alpha S minus 1, and this is 10 raised to 0.1 alpha P minus 1. Your alpha S is 10 dB. You can substitute this as 10. So this is root of 0.1 into 10. 0.1 into 10 is 1. Okay, so 10 raised to 1 is 10. So 10 minus 1, so that is 9. Root 9 is 3. So lambda will be 3. Similarly, substitute alpha p is equal to 2. So 10 raised to 0.2. 0.1 into 2. So that is 0.2 minus 1. So you have to find those values. And you will get your corresponding epsilon value. Okay, have to do that. Now you can find the order. You can substitute the values for this, and the order will be approximately, this value will be actually 3.37. Therefore, this can be rounded to the next higher value, that is 4. So we have fixed the order as 4. The order is 4. So that's the first step, computing the order. Second step is you have to select your transfer function from the table that we have learned. And do remember the denominator was mentioned in that table. Numerator is always 1. Let me write those value. Denominator value was s square plus 0.76537 s plus 1 into s square plus 1.8477 s plus 1. So this is your transfer function. Okay. The peculiarity of this thing is that this is designed for cutoff frequency of 1. We have mentioned it as a note in the previous class. This was done for a cutoff frequency of 1. So this is a Butterworth low-pass filter, but the cutoff frequency is not ours. Okay, it's just 1 only. So we have to convert this transfer function to your desired response. So first I have to calculate my cutoff frequency. So that can be calculated using the equation omega p by epsilon raised to 1 by n, or omega s by lambda raised to 1 by n. So it was mentioned in the question that you have to meet the passband specification. Okay. So even though if it is not mentioned anything, you proceed with the passband specification. And if peculiarly if it is mentioned that you have to follow the stopband specification, or you have to meet the stopband specification, you have to use the other equation, that was omega s by lambda raised to 1 by n, right? So we can use this thing omega p by epsilon raised to 1 by n, and omega p value is how much? 30, right? Sorry, 20. Omega p is 20. divided by epsilon raised to 1 by n. I have not calculated this value, so you can substitute this value, root of 10 raised to 0.1 alpha p. You can find that value. Alpha p is how much? 2 dB. So this into 2 minus 1 raised to 1 by 4. The order is 4, so you can substitute raised to 1 by 4. So solve this. That will be 21.3868. So this is my cutoff frequency. So what can you do right now? I know my cutoff frequency and I know the transfer function. Now convert this transfer function to this particular cutoff frequency. So that is the last step. You have to substitute, or you have to replace S with S by omega C. That will be the completion of the design. Therefore, what will be my H of S? H of S is equal to, in this equation, you substitute. Instead of S, you have to replace S by 21 point, let it be 4. Okay, let me round it to 21.4. So 21.4, the whole square plus 0.76537 into S divided by 21.3868. Or sorry, 21.4, that's enough, plus 1. So there is the first term, into, you will have the second term, this one. So again, there also replace S by 21.4. So square plus 1.8477. As you can simplify this thing, dividing it with this 21.4. Okay, can solve this. That much S plus 1. So this will be your final transfer function. So if you have time in the exam, just solve this and rearrange it. Or else you can simply leave with this step. You can solve these simple calculations and you can leave it out. So this is the design. So what we have designed a low pass Butterworth filter. Okay. So we will see one more problem. One last question from this section. We will do that tomorrow at the last lecture.